Indeterminate forms and L'Hopital's rule. In this section, we are going to talk about various types of indeterminate forms. The first type is the type 0 divided by 0 or infinity divided by infinity. To motivate this, let's consider the following two examples. In the first example here, we have the limit as x approaches 1 of the natural log of x divided by x minus 1. Now, as x gets close to 1, we know that the natural log gets close to 0 because the natural log of 1 is 0. And of course, in the denominator, as x gets close to 1, 1 minus 1 is also 0. So x minus 1 is getting closer to 0. And so this is what we mean when we say 0 divided by 0. Please understand that this limit is not 0 divided by 0 literally. It is something that is getting close to 0 divided by something else that is getting close to 0. And what we want to know is, what does this equal? Well, it could be anything. So as you'll see as we go through examples, sometimes this answer will be 0, sometimes it will be infinity, and sometimes it will be some other number. If you consider the second limit here, we have the limit as x goes to infinity of x squared minus 1 divided by 2x squared plus 1. And as x gets really large, x squared minus 1 also gets very large. And in the denominator, it's the same story. It is also getting very large. And so here we have a limit that is infinity divided by infinity. And again, it's not literally infinity divided by infinity. It is something that is getting large divided by something else that is getting large. And again, we want to determine what does this equal. And again, it could be anything. To help us evaluate these kinds of limits, or these kinds of indeterminate forms, we are going to use something called L'Hopital's rule. L'Hopital's rule says, suppose f and g are differentiable, and g of x is not equal to 0 on an open interval that contains a, except possibly at a itself. Suppose that the limit as x approaches a of f of x is 0, and the limit as x approaches a of g of x is 0. Or suppose that the limit as x approaches a of f of x is positive or negative infinity, and the limit as x approaches a of g of x is positive or negative infinity. In other words, we have an indeterminate form of the type 0 divided by 0 or infinity divided by infinity. So in this situation, the limit as x approaches a of f of x divided by g of x is equivalent to the limit as x approaches a of the derivative of f of x divided by the derivative of g of x, as long as this limit here exists. Let's consider an example. So here we go back to the first limit that we discussed. And so we already know that if you take the limit as x approaches 1 of the natural log of x divided by x minus 1, this limit is in effect 0 divided by 0. And so using L'Hopital's rule, we know that this limit is equal to the limit as x approaches 1 of the derivative of natural log of x divided by the derivative of x minus 1. And anytime I use L'Hopital's rule, I like to put a capital H above my equal sign to indicate that I'm using L'Hopital's rule. Now all we have to do is compute these derivatives. The derivative of the natural log of x, of course, is 1 over x, and the derivative of x minus 1 is 1. And you don't have to simplify this, but 1 over x divided by 1 is the same as 1 over x. And as x approaches 1, we simply get 1 divided by 1, which is 1. So L'Hopital's rule is very easy to use and gives you a result rather quickly in most cases. Now, I need to emphasize this, but you can only use L'Hopital's rule if your original limit is 0 divided by 0 or infinity divided by infinity. If it's not one of those, then you cannot use L'Hopital's rule. So please keep that in mind. For our next example, we have the limit as x approaches infinity, or as x gets larger, of the function e to the x divided by x squared. So once again, I'm going to start by saying if we take the limit as x gets large of e to the x over x squared, we know that e to the x gets extremely large as x gets large, and x squared also gets extremely large as x gets large. So this is a limit of the form infinity divided by infinity. Therefore, this is equal to, using L'Hopital's rule, we can take the limit as x goes to infinity of the derivative of e to the x divided by the derivative of x squared. And if we compute these derivatives, we get the limit as x goes to infinity. Derivative of e to the x is e to the x. And the derivative of x squared is 2x. And as x gets large, this is still equal to infinity over infinity. But the nice thing about L'Hopital's rule is that we can simply treat this as a new problem. And the fact that we still get the indeterminate infinity divided by infinity means that I can apply L'Hopital's rule again. And so now I'm going to take the limit as x goes to infinity of the derivative of e to the x divided by the derivative of 2x. And this, of course, is the limit as x goes to infinity of e to the x divided by 2. And now, as x gets extremely large, this is going to be infinity divided by 2, which, of course, is infinity. And so this limit is infinity, or technically we can say this limit does not exist, but infinity is the better answer. In our next example, once again, we have the limit as x goes to infinity. This time we have the natural log of x divided by the square root of x. And as x gets very large, the natural log of a very large number is also a large number. And the square root of a very large number is a large number. So we do get infinity divided by infinity once again. Therefore, I can apply L'Hopital's rule. I'm going to take the limit as x goes to infinity. And now, rather than putting in the notation here, I'm simply going to take the derivative. So the derivative of natural log of x we know is 1 over x. And the derivative of the square root of x we know is 1 divided by 2 times the square root of x. And so now, if you reevaluate this limit, as x gets large, 1 divided by a large number is going to be 0. And as x gets large here, 1 divided by a large number is also going to be 0. So we could apply L'Hopital's rule again, but actually if we do this, we will get into an infinite loop. In other words, we'll never come out of this with an answer. So here's something else you need to consider when you're applying L'Hopital's rule. If you have an opportunity to simplify the expression that you have here, you should go ahead and simplify it. So what I mean is we could rewrite this as the limit as x goes to infinity of 1 over x multiplied by 2 radical x over 1. And this is the limit as x goes to infinity of 2 radical x divided by x. And we can further simplify this. If you just think about properties of exponents, we can write this as 2x to the 1/2 divided by x to the 1. And this becomes 2x to the negative 1/2 because we can subtract these powers. And then I'll just take the liberty to express this as 2 divided by x to the negative 1/2 becomes the square root of x in the denominator. And this is essentially 2 divided by infinity, which we know is 0, right? If you have a constant divided by something that is getting extremely large, we know this limit is 0. So if you can simplify your expression after applying L'Hopital's rule, you should go ahead and do that. Don't just keep applying L'Hopital's rule when you have an opportunity to simplify. In our next example, we have the limit as x approaches 0 of tangent of x minus x over x cubed. And if you plug in 0, tangent of 0 is 0, and of course here you get 0. So the numerator is getting closer to 0, and the denominator, of course, is also getting closer to 0. So therefore, we can say this is equal to, by L'Hopital's rule, the limit as x approaches 0 of the derivative of the numerator. So what is the derivative of tangent of x? Well, it is secant squared of x minus, and then the derivative of x, of course, is just 1. And in the denominator, we have 3x squared. And now if we reevaluate the limit, secant of 0 is 1. And of course, 1 squared is 1. So in the numerator, we get 1 minus 1, which is 0. And in the denominator, we also get 0, right? As x goes to 0 here, this becomes 0. But unlike the last example, I cannot simplify this, right? There's no way to combine these together to cancel anything. So here, I need to apply L'Hopital's rule again. So we will take the limit as x goes to 0, and now we got to take the derivative of the numerator and the derivative of the denominator. The denominator is simple enough. Its derivative is 6x. But what is the derivative of secant squared? So if you need to, you might want to go off to the side somewhere and evaluate that derivative. So let's remind ourselves that we have secant of x quantity squared, and its derivative is going to be 2 times secant of x to the 1 times the derivative of secant of x, which is secant of x tangent of x. So we get 2 secant squared x tangent x. Okay, so that is the derivative of secant squared. And of course, the derivative of negative 1 is 0. All right, now let's try the limit once again. So as x goes to 0, secant of 0 is 1, but unfortunately tangent of 0 is 0. So the numerator is still 0, and the denominator is also still 0. So we need to apply L'Hopital's rule yet again. So we have the limit as x goes to 0. The derivative of the denominator now, of course, is just 6. But we have to take the derivative of the numerator, and that's going to be a little bit of work. The derivative of secant squared of x times tangent x, and also the 2 here, 2 secant squared of x times tangent of x. We're going to use the product rule here. So we have the first function, 2 secant squared of x, multiplied by the derivative of tangent of x, which is secant squared of x. Plus, then we have the derivative of 2 secant squared. Let me remind you that the derivative of secant squared was right here. So the derivative of 2 secant squared is going to be 2 times 2 secant squared tangent. And then we have to multiply by the second function, which is tangent. And so when we clean this up, we get 2 secant to the 4th power of x plus 4 secant squared of x times tangent squared of x. And that is our derivative now, which we are going to put in the numerator. All right, and now we're going to evaluate this. So as x goes to 0, secant of 0 is 1, so that becomes 2 times 1 to the 4th. Plus, then we have 4 times secant of 0 is 1, so we have 1 squared. And then tangent of 0 is 0, so that's 0 squared. And the denominator is a constant. And of course, this equals 0. And so what we have here is 2 divided by 6, which simplifies to 1/3. So the point of this problem is that you may have to use L'Hopital's rule multiple times. And it can get rather complicated. Those derivatives can get rather complicated when you start having products of functions and also having to use chain rule and things like that. Okay. In this example here, we have the limit as x approaches pi from the left, sine of x divided by 1 minus cosine of x. Now here I want to emphasize the importance of checking the hypotheses of L'Hopital's rule. So what I mean is, don't simply apply L'Hopital's rule assuming that it always works. You must have 0 divided by 0 or infinity divided by infinity. If you don't have one of those, you cannot use L'Hopital's rule. So here, as x approaches pi from the left, sine of pi we know is 0. And in the denominator we have 1 minus cosine of pi. But cosine of pi is -1. And so this is equal to 0 divided by 2, which is 0. L'Hopital's rule is not necessary in this problem, nor would it be correct if you used it. So make sure you have one of these indeterminates before you simply apply L'Hopital's rule. Now let's shift our focus to another indeterminate type. This is an indeterminate product 0 times infinity, which means you will have a limit where one function is getting close to 0 and the other function is getting larger. So as an example, let's consider the limit as x goes to 0 from the right of x times the natural log of x. So first, let's make sure that this limit is of the type that we're talking about here. So, of course, right here, as x goes to 0, that is going to go to 0. But then the second part, natural log of x. What happens to the natural log of x as x approaches 0? So let's remember that our natural log graph looks like this, and it passes through the point here, 1, 0. So as x is approaching 0 from the right, x is moving in this direction, getting closer to the origin. And we can see as that happens, as you get closer to 0 here, the values of natural log are going down, right? And this is unbounded. So the natural log values are going to negative infinity. So what we have here is 0 times negative infinity. And this does fit this indeterminate type. So another just a quick comment here. When we say infinity, that infinity could be plus or minus infinity. Okay, so it does not have to only be positive infinity. So in the case where you have this type of indeterminate, what you want to do is employ a simple algebraic manipulation. And that is right here. So if we're multiplying two functions, f times g, we can write this as f divided by 1 over g, or we can write it as g divided by 1 over f, right? And we know this because of the definition of division. We know that when you divide by 1 over g, that's the same as multiplying by g over 1, which would give us the fg. So that's what we're going to do here. we're going to say this is equal to the limit as x goes to 0 from the right, and then we have to choose out of these two functions. We're going to leave one of them in the numerator, and then in the denominator we will put the reciprocal of the other one. Now what I like to do is keep your more complicated function where it is. So that would be the natural log of x in this case. And then the x here is going to drop to the denominator as 1 over x. Now let's evaluate this limit once again. So we know that as x goes to 0, the natural log of x goes to negative infinity. And in the denominator, as x goes to 0, 1 divided by a small positive number is positive infinity. So now we have a L'Hopital indeterminate, and we can therefore apply L'Hopital's rule. So this becomes the limit as x goes to 0. I'm going to take the derivative of natural log of x, which is 1 over x, and the derivative of 1 over x, which is actually negative 1 over x squared. And again, before I evaluate this, I'm going to notice that I can simplify this by multiplying by the reciprocal. So dividing by negative 1 over x squared is the same as multiplying by negative x squared over 1. And when we cancel the x there, we end up getting the limit as x goes to 0 of negative x, right? Because this x here cancels out one of those. And this limit, of course, is just 0. So when you have an indeterminate product, 0 times infinity, what we do is we employ this technique. We put one of these functions as a reciprocal in the denominator, which will always convert it into a L'Hopital indeterminate, and then we just apply L'Hopital's rule. The next indeterminate type is what we call an indeterminate difference, and it is where you have infinity minus infinity. And just to be clear, infinity plus infinity is not an indeterminate. That is infinity. And negative infinity minus infinity is not an indeterminate. That is simply negative infinity. So it is only when you have infinity minus infinity or negative infinity plus infinity, these are the ones where we don't know what it is equal to. So let's consider the following example here. We have the limit as x approaches 1 from the right of the natural log of x, 1 over the natural log of x, minus 1 over x minus 1. So as x goes to 1 from the right, let's think about what is happening to the natural log. So again, the natural log graph looks like this. And here is the point 1, 0. If x is approaching 1 from the right, we are approaching 1 here. And as we do that, the values of natural log, of course, are getting closer to 0. But what's important here is that these are above the x-axis. And so yes, it's getting closer to 0, but those numbers are going to be small positive numbers. So what that means in terms of this limit is that when we take x approaching 1 from the right, what's happening here is we are getting 1 divided by a very small positive number, because that is what happens to the natural log of x. Minus, and then what happens here as x goes to 1 from the right, again, think about what 1 from the right means. It means we're plugging in very small or numbers that are very slightly greater than 1, like 1.001, for example. And so if I take a number like this and I plug it in, I have 1.001 minus 1, which is, again, a very small number, but it is a very small positive number. And that's important because when you take 1 divided by a small positive number, that is positive infinity. Minus, and then 1 divided by a small positive number again, is again positive infinity. And so this is an indeterminate form. So how do we approach these types of indeterminates? Well, we cannot apply L'Hopital's rule. So what we have to do is try to rewrite this using principles of algebra. So what I'm going to do here is take these fractions, 1 over the natural log of x minus 1 over x minus 1, and I'm going to get a common denominator by multiplying by x minus 1 to the numerator and denominator of the first fraction, and multiplying by the natural log of x to the numerator and denominator of the second fraction. And when I do this, I get the limit as x approaches 1 from the right. We have x minus 1 over x minus 1 natural log of x minus natural log of x over x minus 1 natural log of x. And now that we have a common denominator, I can combine these into a single fraction with the same denominator. And in the numerator, I have x minus 1 minus the natural log of x. And let's reevaluate this limit. So again, as x approaches 1, we get 1 minus 0. So the numerator is clearly 0. And the denominator, as x approaches 1 here, we get 0 and also 0. So we get 0 times 0, which is 0. So now we have a L'Hopital indeterminate, which means in the next step, I can go ahead and apply L'Hopital's rule. So L'Hopital's rule says I'm going to take the derivative of x, which is 1, minus the derivative of 1, which is 0, minus the derivative of natural log of x, which is 1 over x. And in the denominator, we have a product of these two functions. So that derivative will be the first function, x minus 1, times the derivative of the second function. So derivative of natural log of x is 1 over x. Plus, then we have the derivative of the first function, which is 1, multiplied by the second function. And if I simplify this, we have the limit as x approaches 1 from the right, 1 minus 1 over x, divided by x minus 1 over x, plus the natural log of x. Now, if you plug in 1 again, you will get 0 again here, and you will get 0 again here. But I really don't want to take a derivative of this thing. So what I'm going to do is I'm going to multiply the top and bottom by x to get rid of that complex fraction. So that gives me the limit as x approaches 1. I'm going to have x minus 1 in the numerator, right? So when I multiply this and multiply this, and then in the denominator, when I multiply here, the x's cancel, and we get x minus 1, plus, and then x times the natural log of x. Now, when I plug in 1, I'm still going to get 0 divided by 0, but that is a L'Hopital indeterminate, and that means that we can apply L'Hopital's rule again. So we're going to have the limit as x approaches 1 from the right, the derivative of the numerator, so the numerator there is x minus 1, so derivative of that is going to be 1. In the denominator here, we have x minus 1, the derivative of x is 1, and then we have derivative of x natural log of x, which is a product. So we're going to get 1 plus, of course, the derivative of negative 1 is 0, and then the product rule says first function times the derivative of the second function plus the second function times the derivative of the first function. So we're simply applying the product rule to these two functions. And now we should be able to do this limit. It's not going to be a L'Hopital again because we can see the numerator is already 1. And in the denominator, we have 1 plus 1 plus the natural log of x. And as x approaches 1, the natural log of 1 is 0, so we get 1 divided by 1 plus 0, which is 1/2. Next, let's consider a special example. Here we have the limit as x goes to infinity, e to the x minus x, which is clearly infinity minus infinity. But notice that this time there really is no way to combine these together, right? So there's no denominator to speak of to combine fractions like we did in the last problem. So when you have something like this, sometimes you have to try things. And so what I'm going to do here is I'm going to factor out an x. And I know that seems weird because there's no x here. There's just e to the x. But I'm going to factor out this number. Okay, so I'm pulling out this x here. And when you pull an x out of e to the x, you simply get e to the x divided by x. Minus, and then when you pull an x out of x here, you get 1. Now, this, of course, is infinity, and then the only question is, what happens to this? Well, we have to consider this limit separately. So what if we had the limit as x goes to infinity of e to the x over x? We know this is infinity divided by infinity. Therefore, this is equal to, by L'Hopital's rule, the limit of the derivative of e to the x divided by the derivative of x. And this, of course, is clearly infinity. So we now know that this goes to infinity. So this limit is, in essence, infinity times infinity minus 1. And this is infinity times infinity, which is clearly infinity. The final type of indeterminate form is what we call indeterminate powers. So this is when you get a limit that is equal to 0 to the 0, infinity to the 0, or 1 to the infinity. So as an example, let's consider the following limit here. We have the limit as x approaches 0 from the right, 1 plus the sine of 4x to the power cotangent of x. And so as x goes to 0, we know that sine of 0 is 0, so the inside of the parentheses here becomes 1. And then the only question is, what happens to cotangent of x as x approaches 0 from the right? Well, for this, you really need to know the graph of cotangent. And it's okay if you don't, because a lot of times we forget graphs of functions that we don't use regularly. But this is what the graph of cotangent looks like, okay? So if we are approaching 0 from the right, it means that we are moving close to 0 in this manner. And you can see the values of the function are clearly going to infinity. So cotangent goes to infinity as x approaches 0 from the right. So we clearly have the indeterminate form of 1 to the infinity. So how do we deal with it? Well, what we're going to do is use a natural logarithm. So let's remember that if you have some expression, let's just say that you have some number a, you can express this as e to the natural log of a, right? And this is because the e and the natural log cancel out. All right, so what I'm going to do here is I'm going to take the original limit as x approaches 0 from the right, 1 plus sine of 4x to the cotangent of x. But instead of looking at that limit again, I'm going to look at the limit of the natural log of that thing. Okay, so I'm working on this part. All right. So why would we do this? Why would we take the natural log of this? Well, it's all about properties of logarithms. This cotangent of x can now come down in front. And this becomes the limit as x approaches 0 from the right, cotangent of x times the natural log of 1 plus the sine of 4x. Now, what is this limit? Well, as x goes to 0 from the right, we know cotangent goes to infinity. And we already know that this goes to 1, but we have the natural log of 1 now, which is 0. So you see what we get is infinity times 0, which is another type of indeterminate that we talked about earlier. So now what I can do is I can rewrite this limit as the limit as x goes to 0 from the right of the natural log of 1 plus the sine of 4x divided by, and then I'm going to say the reciprocal of cotangent, right? Remember, that's what we did earlier with this type of indeterminate. And one other thing that I will do before I evaluate this, or attempt to evaluate this, is I'm going to recognize that 1 over cotangent is actually the same as tangent. And now if I substitute 0 in here, I get the natural log of 1 on top, which is 0, and of course tangent of 0 is 0. And look at that. Now we have a L'Hopital indeterminate. And so this is equal to, by L'Hopital's rule, we could take the limit of the derivative of the numerator. Derivative of natural log of anything is 1 over that thing times the derivative of that thing. And the derivative of sine of 4x is 4 cosine of 4x. And then divided by the derivative of tangent, which of course is secant squared. And so what I have here now is the limit as x goes to 0 from the right, 4 cosine 4x over 1 plus the sine of 4x, and then that whole thing is divided by secant squared of x. Okay, so we have the limit of all of this. But this limit is not difficult because all you have to do is plug in 0. When you plug in 0, 4 times 0 is 0. Cosine of 0 is 1. So you have 4 times 1 up there, divided by, when you plug in 0 here, sine of 4 times 0 is 0. So you have 1 plus 0. And then that whole thing is divided by secant squared of 0. Well, secant of 0 is 1, so it's just 1 squared. So what we have is 4 divided by 1, which of course is 4. Now, this is the tricky part. 4 is not our answer, right? Because what I did is I took our original limit here, and I took the natural log of it. So the limit of the natural log is 4. But to get our original number back, we have to do e to the natural log. So whatever you get for this limit in the end here, this 4, the actual limit of what we're looking for, which is this original thing here, this limit is going to be e to the 4th power. Okay? And again, the reason we're doing e to the 4th power is because e cancels the logarithm that we took earlier. All right. So this last type takes a little bit more practice than the others, in my opinion, but with practice, it's not too bad. And that concludes this video lesson.